Okay, for this question, we are first going to start by finding the binary value of positive 7.25. As we know, because it's positive, the most significant bit has to start with 0, otherwise it'll be negative, using 2's complement. Then we put 3 ones in, as we know that this value is 1, 2, and 4, which add up to 7. Then after the decimal point, we put 0 and 1, as we know that the first value here is 0.5, and the second value is 0.25. So this equals 7.25. Then, using 2's complement, we find the negative value of this number. So to find minus 7.25, from the right side, we go until the first 1 and keep it. So 1, then all the other bits, we swap them around. So 1, 0, 0, 0, and 1. Make sure to keep the decimal place in there as well. Then you have to move the decimal place to the first area on the left, where in between the first 2 bits that are different. So 1 and 0 or 0 and 1. It cannot be the same, otherwise it's not normalized form. So we shift this along 1, 2, and 3. Then we would put the decimal place right here. And because we have shifted it along 3 places, we know that the exponent has to equal 3, which in binary is 0, 1, 1. Remember to put the 0 at the beginning to make it positive. Now when we put it in, we're going to have to fill up all the unused bits in the boxes. So we start off by putting in the current bits that we use and just fill the rest up with zeros, so the boxes are not empty. And we use the same with the exponent, so we can write in the value here and we just replace with zeros at the end, and these do not change the values. Now for part B, we want to calculate the denary value of this float point number. So first we're going to calculate the exponent, which, as we know from general binary rules, this is 1, 2, and 4. Therefore 1 plus 2 plus 4 is equal to 7. Now we always assume that the decimal point is here in between the first 2 values in the mantissa, and we're going to use 2's complement to convert it, as it is currently negative. So as we said from before, go from the right side up until the first 1, keep all them the same, and the rest we're going to flip. So we go up to the first 1, which we get 1, and then we flip the others. So 0, 0, 1, 1, 1, 0, 0, 1, 0, and make sure to keep the decimal point in there. Then we know that the exponent is 7, so we're going to shift the decimal place 7 times. So 1, 2, 3, 4, 5, 6, 7, which is right here. So now we rewrite the number with the shifted value. Now we can calculate this as normal, which we have 64 here plus 8, 4, and 2. So 64 plus 8 plus 4 plus 2. Then for the decimal value, we have 0.25, and add that on here, which then will give us 78.25. But as the value the mantissa starts with a 1, we know it's negative, so the answer will have to be negative 78.25. Now, for part C, we have to normalize this, which means we have to get the decimal place in between the first 2 different bits. So currently, the decimal place is right here. However, this is in between a 0 and a 0, which is not correct. We want to be into the first area where it's a different number, so either 0, 1 or 1, 0, which will be here. So if we assume we want it here, and it is currently here, we will have to shift the bits along, shift the decimal point along 1, 2, 3, 4, 5, 6 times. Therefore, we know the exponent is going to equal 6. which shift it along 6 times, which is 0, 1, 1, 0, because it is positive, always start with a 0. Then we have the current exponent, which is 1, 0, 0, 1, 1, 1. If we take away this 6 for the exponent from that, then that value will equal this. So we know the exponent is going to have this value, and then we start from the mantissa, from where we've now put the decimal place, which is right here. So we start with 0, 1, 1, 1, and we fill the rest in with zeros. Now for part D, the value 315 cannot be used as currently for this mantissa. There is 10 bits being used. So when using 10 bits for the mantissa, the maximum value that you can get from this is 511, which is obviously less than 513. Therefore, you would need 11 bits for the mantissa. To be able to have it in a normalized form, because we can store the value, we need to store the value one, 2, 3, 4, 5, 6, 7, 8. This is the way we'll store the value. This is 513 in binary using floating point representation. And therefore, if you were to try to store it in the current mantissa, the value would not be able to store it, and there would be overflow. Now for the final part, the way that we can change this is either increase the number of bits used in the mantissa, or we currently have a 10-6 split for the mantissa and exponent. And so we can just change the split. So if we need now 11 bits for the mantissa, we can have the mantissa side have 11, and now, because we're still using 16 bits in total, we will have a 11-5 split with 5 being the exponent.